This lesson, this first page, looks like it was in the last page, but I am highlighting something different about this bridge. Remember, in this bridge we looked at similar triangles in this. But I also want you to notice that there are right triangles in this bridge. And if you draw from one of those right triangles to the other side, that forms two new right triangles. If you draw from that to another side, there's two new right triangles there and two more right triangles there. We can also notice that all of these right triangles that are formed are similar triangles. And so there's relationships that we can exploit from that and use to find missing sides when we have parts, when we're drawing the altitude in these. So if I take a rectangle, remember we can draw a diagonal and get two congruent triangles here. If I pull these apart, we'll notice that these are all similar triangles. Maybe we'll need to turn them a little bit. And this one would maybe need to be flipped over, but we can see those similar triangles in there. So the important thing is noticing that what we're looking at is going from a right angle and we're drawing the altitude from the right angle. So we're drawing the altitude to the hypotenuse, the longest side. And in that, that's going to give us all these similar triangles. And so the theorem we get is that we get these similar triangles when we pull that apart. So to prove that theorem, let's look at the angles that we have here. If I start with looking at angles 5 and 6 here, notice that that is a right angle there. So the measure of angle 5 plus the measure of angle 6 is going to be 90 degrees. Now we can also notice, looking at this green triangle, since we have a right angle here at 9, that these two angles would also have to add up to 90 degrees. Because of the right triangle, we need 180 degrees there. And we could also look at the larger triangle. If I look at angle 7 and 4 there, those would also have to be 90 degrees. So we can pull some information out of that. Notice, since these 5s are the same, that must mean that the measure of angle 4 and the measure of angle 6 are equal to each other. And therefore they're congruent. We can also look at the second pair. Since I have 4 twice here, I can notice that 5 and 7 must be the same. And so when I pull these triangles apart and we look at the matching angles, we should be able to see that angle 5 is congruent to angle 7 and congruent to angle 7. Those three are all congruent angles. We could also look up at angle 4 and 6 here and here, and all of these angles in these triangles are the same. And so by angle, these triangles are all similar to each other, and we could also get matching parts from that. We have proportions with the sides. So if we want to identify the similar triangles, we could either use that theorem, or sometimes it's easier just to redraw the triangles. Redraw the big one, the medium one, and the small one so that they're all facing the same direction. And by drawing them in the same direction, it'll help us label these and see how they're similar. So first, looking at the larger one, ZYX, we notice that the Y's here, we can just label it exactly as it is in the other picture. But what I really want to look at is where the right angles are. So in the medium one, that would be this one over here, the W is up there at the right angle. And the right angle is also the same for the smaller one, that's also at W. We next want to look at where the smaller angle is. Okay, so here I've got that smaller angle in Z, and that's going to be the same for this one here, that's going to be Z, but in the little triangle, that smaller angle is going to be at Y. And then we'll look at the larger of the two non-right angles, and in the biggest one, that's going to be up at X, which we've already got marked, and it's also going to be up at the top for the smaller one. But in the medium-sized one, that angle would actually be down here at Y. So looking at this, we should be able to see how they're all arranged, and we can write a similarity statement for this. I can say triangle ZYX is similar to triangle, look at the next one, ZWY, which is similar to triangle YWX. This would also allow us to match up congruent angles and corresponding sides for proportions. The next thing that's presented to us is a little bit of vocabulary, something called the geometric mean. And really what it is just a way of looking at numbers. If they say the geometric mean of A and B, we would be looking at some number x where we can put in a proportion like this. Notice A and B are on the extremes of this, and then we have the same number on either side here. So they say, what is the geometric mean of, so the geometric mean would be our x of 4 and 18. So we're going to set up a proportion where x is on the bottom on one side, on the top of the other side. Basically, the geometric mean between the two numbers, so it'll be like this. When I cross multiply, that's going to give me x squared equal to 72. If we take the square root there, we can't take the square root of 72, but we might notice that we can get 36 times 2, allowing us to pull out a 6. And so x, the exact answer would be 6 square root of 2, or we could use our calculator and plug that in and get about 8.5 for our geometric mean. Now sometimes it's better to have an exact answer for these, so it's good to remember your algebra skills and simplifying radicals. So we're going to use the geometric mean with our right triangles because there's a relationship, first of all, between our altitude and the parts of our side. Okay, so the altitude is going to split the hypotenuse into two parts, and so we can always set up a geometric mean where the altitude is the geometric mean between them. Okay, again, the altitude, the geometric mean between them. So we'll see that in a problem like this. We've got RS, okay, so we should label that SQ or QS 14. And we want to find PS right here, so I'll call that my x. Now from our theorem, the altitude is the geometric mean, so I will have 3 over x equals x over 14. That's going to give me x squared equals 42. X is the square root of 42. And that can't be simplified, but we can put in our calculator and round it to the nearest tenth. So either one of these answers would be fine. So you might ask the question, do I have to memorize this? Meaning, do you have to memorize the formula? Well, not exactly. Remember that we can pull this thing apart and think about all of these triangles as being similar. So if I think about the smaller one and the medium-sized one, the two parts inside the larger one, we could draw them like this. Notice that the smaller one, if I turn it, it's going to be 3 on this side, x on this side. The medium-sized one will have x on this side, 14 on this side. That'll allow us to set up a proportion where I have 3 over x equals x over 14, giving me the same thing as my formula. So this formula, if we remember that, it's going to be a shortcut. But if you forget that, we can always remember the basic idea of this lesson, that we have similar triangles. Now there's another formula that will come this, corollary 2 here, that this time we're looking at a side, one of the legs of our big one, the small part of the hypotenuse, and the whole hypotenuse. We can set this up with the smaller part of the hypotenuse over the leg, and then the leg over the whole hypotenuse. So again, remember that the leg is our geometric mean. That's our x in this one. We could also do the same thing using this side over here. If I had, maybe call this y and b, since this is the part that corresponds with y that's matching there, we could write this as b over y because y is our leg, and y over the whole hypotenuse, h. And when we see a problem like this, we need to look carefully to check which corollary we're actually using, whether we're using the one that involves the altitude or the one that's using the leg. So in this one I can see if I'm looking for x, then that's a leg, so it's going to involve a part of the hypotenuse of the larger one and the whole side. And so using that one, using x here, using corollary 2 that we've just looked at, we're going to take x as our geometric mean. We take the small part 4 over our leg x, and then we take x over the whole side. So we're going to need to take that 4 and that 12 to get the whole side of 16. If we cross multiply, that gives us x squared equal to 64, and so x is equal to 8. For the other, we're going to look at y. So this is going to be going back to corollary 1. We've got this picture here. And so what I need are the two parts of the legs, the 4 and the 12, and that y will be the geometric mean between them. So 4 over y is equal to y over 12. That gives us y squared is equal to 48. So we can take the square root of both sides, giving us the square root of 48. 48 isn't a perfect square, so we can simplify that to 16 times 3. 16 is a perfect square, which you could write as 4 times the square root of 3. If we wanted a decimal value for that, we could put it into our calculator, or we can just leave it like this. In our last problem, we look at a real way that this could be used in the real world. Notice what he's doing here. He's got this little instrument that's basically giving him a right angle where he can look up the side, and he's lining that up so he sees the top of the train, and the bottom side he's lining up so he can see the base of this figure here. And we should look at where these parts line up here. He's drawn this line straight. Notice that's parallel to the ground to get this altitude here. So the distance from his eyes to where we're drawing this height of the train would also be 8.75. We can also bring over his height from his feet to his eyes, and that would go right here, 5.5. Now we are looking for the height of the train here, h. But if we notice the triangles that we're doing, notice we have the altitude here, which means the theorem I need to use is the one connecting the parts of the hypotenuse. We're not going to be using this side, which would allow us to use the whole hypotenuse, so I'm going to call this part x for now. Because if I know the parts of the hypotenuse, I can use 8.75 as our geometric mean. So if I start with x over 8.75, then that will be equal to 8.75 over 5.5. Now we can solve this equation, and that will give us x is about 13.9. Now be careful, we're not finished with this. We wanted to find the train's height, but we selected x just to go from z to x here. So we need to find the height here. The height is going to be x plus 5.5. We rounded that, so we're going to say height is about 13.9 plus 5.5. This is going to give us a height of about 19.5. Now since they've given us units, be sure to put units in your answer, and that's measured in feet.